We're going to start with the lecture notes from last Friday because I didn't finish them. What we were doing at the end of lecture last time was probably some of the hardest concepts that we've covered so far in this course, and maybe even in the whole course. And you'll remember that we finally got around to talking about what does a wave function mean? How does it actually represent the electron in our hydrogen atom? And we saw that the physically significant interpretation of the wave function was not actually the wave function itself, but the wave function squared. So psi here, which we learned has to be labeled by 3 quantum numbers, n, l, and m. And that is a function of 3 position variables, r, theta, and phi. If you square that, the physical interpretation of that is a probability density. This means this has units. This has units of inverse volume. Right? It's a probability per unit volume. That's very important. It's not a probability, but a probability per unit volume. But the other quantity that we would like to know something about is a probability. We'd like to know something about how far is the electron from the nucleus. And in order to do that, we needed to invoke this concept here, this radial probability distribution function. And what we said it was last time is a probability of finding an electron in a spherical shell of radius r, and that spherical shell has a thickness dr. Or another way to say it is that it's the probability of finding the electron at a distance between r to r plus dr. Okay, now this is a probability here. And we illustrated that in the following way. This gray portion here, well, that was our dot density diagram. That gray portion was the probability density, right? Psi squared. In this particular case, the 1, 0, 0 wave function, the 1s wave function, we squared it. And then we represented the magnitude of that by that dot density diagram, where the density of the dots, where that was highest, that represented the highest value of psi squared. And then it radially dissipated exponentially. Okay, that's what that gray dot density diagram was. And now, if we take a spherical shell and we put it right at the origin, right, where our nucleus is, and that spherical shell has a radius r, and since it's a shell, it's infinitesimally thin, right, so it has a thickness dr here. The probability of finding the electron in that spherical shell is what the radial probability is. Okay? So it's going to be able to tell us how far, or the probability of finding the electron between r and r plus dr. Okay. Now, how do we calculate the radial probability distribution? Or how do we calculate the radial probability? Well, the first thing you have to realize is what the volume of this spherical shell is, right? The volume of this spherical shell is just the surface area of the sphere, 4 pi r squared, times the thickness, dr. So that's the volume of the spherical shell. Now, what can I do to calculate the radial probability? Well, we know that psi squared is the probability density, probability per unit volume. If I multiply it by that unit volume, in this case 4 pi r squared dr, hey, the volumes here cancel, and we have a probability. That's our radial probability. All right? And this is strictly correct for s orbitals only. There's a little difference here for the p orbitals and d orbitals. We're actually not going to do that. All right? But this is our radial probability. So let's take an example. Let's look at an example of the radial probability for the 1s state. So what have we done here to calculate radial probability? We've taken psi squared. We've squared 1s wave function. And we've multiplied it by 4 pi r squared dr, right, for all these values of r. So we've calculated psi at all the values of r and multiplied it by 4 pi r squared dr. And the result is this radial probability. All right, that's what I'm plotting right here. What do you see? Well, the first thing you see is that the electron, the most probable value of r, or the most probable distance of the electron from the nucleus, is quite a ways out. That most probable value is all the way out here, where r is equal to a naught. And I said last time that this a naught is a constant. It's called the Bohr radius, and today I'll explain why it's called the Bohr radius. But it has a value of 0.529 angstroms. All right? So it's most likely to find the electron about a half an angstrom away from the nucleus. All right? The most probable value, or the most probable position of finding the electron, is not at the nucleus. And in fact, hey, look at this. In fact, that radial probability here is actually, let me focus my pointer, there you go, is actually 0 at r equals 0. Hey, that seems a little strange because we looked at the probability density. Remember, we plotted the probability density the last time, which was just psi squared for the 1, 0, 0 wave function as a function of r. And when we did that, we saw that at r equals 0 here, the probability density was some large maximum value, and that this exponentially decayed. Well, the probability density is a large maximum value at r equals 0, but when we look at the radial probability, it's 0 at r equals 0. Why? Well, because when we go to calculate the radial probability, we are multiplying that probability density by a sphere. A sphere whose volume now has shrunk to 0 because r is equal to 0. All right? So the probability of finding that electron right at the nucleus between r equals 0 and r plus dr is 0. All right? So the most likely distance of that electron in the hydrogen atom from the nucleus is 1 Bohr radius. And actually, then the diameter of that hydrogen atom, we typically say, is twice the Bohr radius, or a little bit over an angstrom. Okay? All right, so that's what a radial probability distribution function means. All right, it's going to tell us the probability of finding the electron a certain distance, r to r plus dr, from the nucleus. All right, but now I want to explain to you where this A naught comes from. And I want to, and that allows me then to also explain a very important concept here about quantum mechanics. 1911, by 1911, both the electron and the nucleus had been discovered, and scientists were trying very hard to understand how the electron and the nucleus hung together, and it wasn't really till 1926, when Schrodinger wrote down his wave equation, that things really began to make sense. But there were many attempts in between 1911 and 1926 to understand what was going on with the hydrogen atom. And one of those attempts was made by Niels Bohr. And, spell this backwards. I think it's N-I-E. Okay. And what Bohr said is, well, okay, I know this classical physics predicts that this electron will plummet into the nucleus in 10 to the minus 10 seconds. That is, if I take a planetary model, I put the nucleus in the center, and I give the electron a uniform circular orbit around that nucleus, well, I know classical physics tells me this won't hang together. But let me ignore that. And let me propose that there's something quantized about the hydrogen atom. And he knew that because he knew the hydrogen atom spectrum. He knew that in the hydrogen atom spectrum that light was emitted at only certain frequencies, as we saw the other day. And that gave him the idea that there's something quantized about the hydrogen atom. So he then proposed, okay, let me go and I'm going to quantize the angular momentum of that electron going around in this circular orbit. So what he did is he kind of took a classical model and he pasted some quantum mechanical ideas onto the system. All right? And when he did that, the value for R here, at which the electron was going around the nucleus, well, that value of R ended up being what we call here the Bohr radius now, this value of A naught. Okay? Now, we're not going to study the Bohr atom because it's wrong. All right? And in particular, what it gets wrong is the radial probability distribution. Okay? Here's the radial probability distribution function as it comes out of solving the Schrodinger equation for an electron in this 1s state. But here's the radial probability distribution function for what's called the Bohr atom. The radial probability, I'll just write it as RPD. The radial probability here is going to be a whopping 1 right at R equal A naught. That's the radial probability distribution for the Bohr atom. What that tells us is we know exactly where the electron is. What that tells us is that we know exactly that the radius of that electron in that stable, in that circular orbit is A naught. Okay? This is what we call a deterministic picture. That is, we know exactly where the electron is in terms of its radius. However, we now know that what's really going on is that we don't know exactly where the electron is. We can't tell you exactly what the radius is. The best we can tell you is a probability of finding the electron within some value R to R plus dr. Quantum mechanics, this is a quantum mechanical result, is non-deterministic. We are limited in the precision with which we can tell you where something is, like the electron. We're limited within the uncertainty principle. The uncertainty principle is not something that we're going to be discussing here, but the uncertainty principle does give us a limit to which we can know the position and the momentum, say, of a particle. All right? So that's really the big point here, is that quantum mechanics, the best it can do for you is to give you a probability of finding the electron at some position. Classical mechanics, which was really this Bohr atom approach, classical mechanics will tell you exactly where something is, right? But not in quantum mechanics. Okay? Very important difference here. questions? Okay. Yes?
So why do you use the full radius then?
Well, it does turn out that if you go to take this distribution function and you actually look at the value of r that at which this is a maximum, it comes out to be exactly that number, a naught. Okay? That actually, there's more to the story in the sense that that is an accident of the particular form of the Coulomb potential that Bohr was able to get this value a naught. Right? So this value really is a naught. Okay? That most probable value. And so you saw we wrote all of our wave functions in terms of that constant a naught. So certainly Bohr made a contribution. He realized, hey, you know, there's something quantized about the hydrogen atom. But he, in order to get that, he kind of pasted the idea of quantization on a classical model. In contrast, in Schrodinger's equation, when we solve it, we talked about how when you have a differential equation, you have to apply boundary conditions to the problem. Well, when you apply the appropriate boundary conditions, the quantum numbers drop out. You know, you're not doing an ad hoc kind of pasting of a quantization ideas onto some model. Okay? Okay. Other questions? All right. Now, so that's the radial probability distribution function for the 1s wave function. But we'd also like to look at the radial probability distribution function for the other s wave functions that we've looked at so far. All right? And let me go over here. And the next one that we're going to look at is for the 2s wave function. All right? So this will be the radial probability distribution function for the 2s wave function. This is versus r. All right? And if I plot it, what I'm going to see is something that looks like this. All right? Lo and behold, the most probable value here of r, RMP, this most probable value, let me get my chalk. All right, I'm going to do it. Okay, the most probable value here, RMP, is actually 6a naught. Hey, it is most likely for the electron in a 2s state to be 6 times as far from the nucleus as it is in the 1s state. Right? That's what the radial probability distribution function tells us. So, if you have a hydrogen atom that is in the first excited state, that hydrogen atom, in a sense, is bigger. It's bigger in the sense that it is more likely to find the electron a further distance from the nucleus than it is in the n=1 state. All right? The other interesting thing here about this radial probability distribution is that you can see where the node is, where the radial node is. Right? We talked about the radial node last time. This is r equal to a naught. A radial node is the value of r that will make your wave function be equal to 0. So that's the radial node. Now, very important here. This r equals 0, r equals 0 is not a radial node. R equals 0 is never a radial node. This gets students into trouble. So let me emphasize this over and over again. R equals 0 is never a radial node. Okay? This r equals 0 right here is a consequence of our definition of the radial probability, 4 pi r squared psi squared dr. That's not a radial node. Okay. What about the 3s wave function? Let's look at that. So this is a radial probability distribution for the 3s wave function. what that distribution would look like is something like this. Hey, look at where the most probable value of R is here. This most probable value is 11.468 A naught. It's about 11.5 times as far out from the nucleus as it was in the case of the hydrogen 1s state. So if you have a hydrogen atom in the second excited state, in a sense, again, it is bigger. It's bigger in the sense that it's more likely to find the electron at a larger distance from the nucleus. Okay? And again, the radial probability distribution function reflects the two radial nodes in the 3s wave function. There's a node here at R equal 1.9 A naught, and there's a node here at R equals 7.1 A naught. Okay, the two radial nodes for 3s. And there's no radial node here at R equals 0. This is really important. Okay? All right. Now, if you look at this, it's very tempting to look at this radial probability distribution function and say the following. Well, if the electron has some probability of being over here, and then it has some probability of being over here, and then it has some probability of being over here, then how does the electron get from here to here to here if this point right here at R equal 1.A naught and R equals 7.1 A naught, how does it get there if these points, the probability is 0? Well, you say, well, or maybe the probability is just small, it's not 0. Hey, but I'm telling you that probability is 0. Zip. Zilch. Nada. Nix. Cipher. Not. Anybody else got a goose egg? Anybody else got another one? It is 0. It's not small, it's just 0. Okay? So that's an interesting question. And the answer to that question is that it's not an appropriate question. Okay? It's not appropriate because when you ask how does a particle get from one place to another place to another place, right? What you're asking about is the trajectory of a particle. You're asking for a path. How does it get from here to here to here to here? That's a classical idea. Right? And this is not a classical system. So that's why the question isn't appropriate. So instead, what we have to think about this as is a wave, right? The electron is represented by a wave. And you know that a wave can have amplitude at many values of x, or at many distances, right? It can have amplitude, and it does right here, at the same time that it has amplitude here, at the same time that it has amplitude there, right? That's the answer to that question. You have to look at this electron as a wave that can have amplitude at many different positions simultaneously. I know that seems strange to you, but you know, this is a different world. This is a world that you don't have everyday experience with. That's why it seems strange. But it is part of our world. It's just a world that you've got to do some experiments to actually see. Okay? Yes?
But if the wave is going through, then wouldn't it pass through that point where it has no probability of existing?
Okay. What I'm talking about here, and this I didn't emphasize, I'm talking about something called a standing wave. All right? You're thinking about a traveling wave. All right? One thing I think I forgot to tell you the last time is that the wave function is, in general, a function of r, theta, phi, and time. Okay? But what I forgot to tell you is that we were not going to look at the time dependence of these waves. And the reason is because we're going to be looking at a hydrogen atom as a hydrogen atom that isn't undergoing any chemical reaction. So its electrons, or the electron of the hydrogen atom, is bound to the nucleus, and it stays there in a sense, right? It is stable. We're not going to be looking at the wave function as two hydrogen atoms come together and make a hydrogen molecule. Then, if we were doing that, we'd have to invoke the time dependence. But because we're going to start here by looking at a hydrogen atom, helium atom, etc., an isolated, stable atom, there's no time dependence here. So we're actually looking at something called stationary waves, right? And that has no time dependence in it. Okay. So this is called time-independent or stationary wave quantum mechanics, time-independent quantum mechanics. There is time-dependent quantum mechanics. Okay.
So why does the electron choose to be at a farther distance from the proton, even though they're coulombically attracted to each other?
Ah, that's a very good question. And it doesn't choose to stay in the 3s state very long. Okay? That is an unstable state. So in other words, if we put the electron in that 3s state, and we have to put energy to do that, that electron does want to be in the more stable state, which is the 1s state. And there will be a probability of that electron dropping down to the 1s state, emitting in a photon, just like we saw in the hydrogen atom discharge experiment. We put those hydrogen atoms into these excited states. They didn't stay there very long, right? They dropped down, and when they did so, they emitted a photon. And there's some natural probability of that happening. In the case of the hydrogen atom, those lifetimes are, depending what state you're in, if a very high Rydberg, they have long lifetimes, but for 3s or something, maybe 10 to the minus 10 seconds, 10 to the minus 11 seconds, doesn't last there very long. Okay, it does emit. Okay, it does come down. It doesn't want to be there for a very long time. And what that probability is has to do with the overlap of the wave functions between the initial and the final state, which isn't something that we're going to do, but well understood. Okay? Okay. So now it's actually time to look at the p orbitals. So with the s orbitals, we saw they were spherically symmetric. And saw they were spherically symmetric. And we used those s orbitals to illustrate a lot of concepts, what we meant by a wave function, what we meant by probability density, what we meant by radial probability. But now we're going to look at the 2p wave functions. And the p wave functions, as you probably already know, are not spherically symmetric. We're going to use this dot density diagram again to represent the probability density for the p wave functions. And so I'm going to take the psi 210 wave function, and I'm going to square it to get the probability density. And then I'm going to plot the result of that in 3 dimensions. And the result is what I show you here. And of course, this is the typical PZ orbital that you've all seen before. And what you see in the case of the PZ state, or the PZ wave function, is that the probability density is symmetric around this z-axis here. Most of that probability density is concentrated along the z-axis. And if you look very carefully, you can sort of see that there's no probability density here in this xy plane. Here's the px orbital. I'm plotting the probability density. That probability density is concentrated along the x-axis. It's symmetric along the x-axis. And if you look very carefully, you can see that there's no probability density in the yz plane. And then the py orbital. That probability density is concentrated along the y-axis. If you look very carefully, there's no probability density here in the xz plane. And the other thing I just wanted to note is you see I got this plus sign here and the minus sign there, plus sign there and the minus sign there. Okay, that we talked about the other day just very briefly. That just indicates the sign of the amplitude of the wave function, not the wave function squared, but the wave function itself. Remember, sometimes it's called the phase. So in this part here, below this xy plane, the wave function actually has a negative value. In this part, the wave function has a positive value. And I said that the sign of the wave function was going to be important because when we start to make bonds, whether you have two wave functions that are overlapping and they have a positive amplitude, well, then you have constructive interference and you have bonding. If you've got two wave functions that overlap and they have opposite signs, hey, you're going to have destructive interference and you're not going to have bonding. So that will become important later on in the course. Okay, but now, as I started to point out as I went through here, what we've got are nodal planes. We've got planes here in which there is no probability density because there's no wave function. All right? And nodal planes are a consequence of angular nodes. Angular nodes are values of theta and phi that will make the wave function be equal to 0. So radial node is a value of r that makes the wave function be 0. Angular nodes are values of theta and phi that make the wave function be equal to 0. And the consequence of an angular node is that you have an angular plane, that you have a nodal plane. So, for example, in the case of the pz wave function, when theta is equal to 90, that makes the wave function be 0. And theta equals to 90 corresponds to everywhere on this xy plane. In the case of the px, when phi is equal to 90, if you plug it into your px wave function, you'll find you'll get 0. And when phi is equal to 90, that means everywhere on the yz plane, you have 0 wave function. And same thing here for the py wave function. Phi is equal to 0. That means everywhere on the xz plane, you have the wave function be equal to 0. All right? So these nodal planes, the angular nodes, are consequences of values of theta and phi that make the wave function be 0. All right, now, in general, and this is something you really do have to know. In general, the total number of nodes that a wave function has is always n minus 1. It's given by the principal quantum number minus 1. The number of angular nodes is always given by the angular momentum quantum number, L. So if L is equal to 1, you have a p wave function. You've got one angular node. And so therefore, if L is the number of angular nodes, and n minus 1 is the number of total nodes, and you only have angular and radial nodes, well then n minus 1 minus L is the number of radial nodes. All right? So the only thing you have to remember is L always gives you the number of angular nodes, and you have to remember n minus 1 is the number of total nodes, and then you can always just figure out that n minus 1 minus L is the number of radial nodes, right? Okay. So, for example, here, 2p orbital, number of total nodes, 1. Number of angular nodes, 1. Number of radial nodes, 0. Okay, you got to know this. And the other thing you have to know is you have to be able to go the other way around. In other words, if I ask you, I tell you a wave function has so many angular nodes and so many radial nodes, tell me what the possible wave functions are. Okay? So you got to be able to go both ways here on this. Okay. So if we've looked at kind of the shapes of these p wave functions by looking at the probability densities, but there's another aspect of these p wave functions that I want to look at, and that is that I want to look at their radial probabilities. I want to look at the radial probability distributions for the p wave functions and compare those to the s wave functions. And so I've plotted here the radial probability for the 2s. We just looked at that. And I plotted here the radial probability for the 2p wave function. Again, the radial probability here at r is equal to 0 is 0. And for the 2p wave function, you can see that there is no other radial node. A 2p wave function doesn't have a radial node. You can see that reflected in the radial probability distribution. But the point I want to make right here is this, that the most probable value of r for an electron in the 2p state, it's actually a little closer in than the most probable value of r for the 2s state. All right? As the angular momentum quantum number goes up, on the average, the electrons are a little bit closer in to the nucleus on the average. Okay? Here's the radial probability for 3s that we looked at. You can see the two radial nodes here, one here, one here. R equals 0 is not a radial node. Here's the radial probability for the 3p state. You can see in 3p we got one radial node right in here. Okay? This is not a radial node. And here's the 3d state. We didn't look at the probability density for 3d. You will look at that with Professor Drennan in the second half of the course when we talk about transition metals. But here you don't see any radial nodes. You see an r equals 0, but that's because of our definition for the radial probability distribution. But again, the point I want to make is here's the most probable value of r for 3s. Here it is for 3p. Here it is for 3d. Hey, again, the most probable value of r for 3d is a little smaller than it is for 3p, is a little smaller than it is for 3s. Okay? So in general, as the angular momentum quantum number goes up, the electrons are a little bit closer into the nucleus. However, and this is important, only in the s orbitals, or the s states, is there really a substantial probability of being very close to the nucleus. Because look, it's only in the 3s or the 2s do you have really some probability that's very, very close to the nucleus. You don't have that in 3p or 3d or 2p. Okay? So there's kind of an irony here. It's only in the s states that you have a considerable probability of being really close to the nucleus. Right? But in general, as you increase the angular momentum quantum number, the most probable value of r comes in closer to the nucleus. All right? So we've got two competing factors there. Now, this information on this slide here might seem to you kind of like it's unattached, and why is she telling me this? And I understand that that's probably how you feel at the moment. But I have to tell it to you now because next time we're going to use this information to understand the behavior of atoms. All right? So this information is going to be important. We're going to refer back to it in the next few lectures. Okay. So we're done at the moment for what we're going to say about the hydrogen atom. And now it's time to move on to multi-electron atoms. And we're going to start here with helium. Well, the Schrodinger equation, of course, correctly predicts the atomic structure of all atoms, right? But the difficulty is that as you increase the number of electrons, the problem, the differential equation that you have to solve gets more and more complicated. And there is no nice analytical way to solve that equation, which means that there's not going to be a nice analytical form, for example, for the allowed energies of a helium atom. That is, we're not going to get an expression of E sub n equal to minus R sub h over n squared. This is a nice analytical expression for the hydrogen atom energies. We're not going to get that for helium. All right? So if you solve the equation for helium, what you actually have to do numerically, what you're going to get is a list of numbers. And you're not going to get a nice analytical form for the wave function. What you're going to get is the amplitude of the function as a function of r, theta, and phi, another list of numbers. Okay? But the truth is, as you increase the number of electrons in the system, you very quickly, by the time you get to 3 and 4, run into such a problem that you can't even solve the Schrodinger equation exactly, even numerically. Okay? Why? Well, here's the example. Here's helium. Here's the Schrodinger equation for helium. I didn't write out the Hamiltonian precisely. I just wrote it the general Hamiltonian. But what I want you to see is that the true wave function for the helium atom would be a wave function that had 6 coordinates in it. 2 values of r for each one of the electrons, electron 1, electron 2. 2 values of theta, 2 values of phi. Hey, we already have 6 coordinates in that wave function in the case of helium. And as we go to lithium, beryllium, boron, hey, the number of electrons, these wave functions, the number of coordinates, it just goes up exponentially. And so in order to solve this equation, we're going to need some approximations. And we're going to talk about the most basic approximation that there is, and that is called the one-electron wave approximation, or the one-electron orbital approximation. And here's the essence of that approximation. What we're going to do is we're going to take that wave function, and then we're going to assume that that wave function can be factored into a wave function for electron 1 times a wave function for electron 2. All right? So it's a one-electron wave. Each electron gets their own wave in this approximation. We're going to make a further approximation. And that is that we're going to give the functional form to electron 1 in the helium atom. We're going to give it a functional form that looks like that of an electron in hydrogen. We're going to give it the psi 100 wave function. Same thing for electron number 2. Or an alternate way to write that is 1s1 times 1s2, where this refers to electron 1, this refers to electron 2. And a more shorthand way is to write this as 1s2, 1s squared. Okay, so that's the approximation for helium. Let's just carry it out for lithium. Well, here's what the wave function would look like. Function of 9 variables, but we're going to give each electron its own wave function in this approximation. And again, we're going to say electron 1 has the 1s hydrogen wave function, electron 2 has the 1s hydrogen wave function, and electron 3 has the 2s hydrogen wave function. Another way to write that is 1s2, 2s. Do you have a question over here? Can I help you? Okay. How about beryllium? 16. But we're going to use our approximation again. One electron is 1s, 1s, 2s, 2s. Way to write that, 1s2, 2s2. Hey, and we can keep going. And when I keep going, you go, oh, I've seen this before, right? You've written down the electron configurations for all of the atoms in the periodic table. Here they are. You know what those electron configurations were that you wrote down? Hey, they were just the shorthand notation for the one electron wave function approximation to solve the Schrodinger equation. That's what those were. Okay? That's it. Nothing more. Okay. But now, what you do notice is that when I got to boron here, I didn't give all 5 electrons the 1s hydrogen wave function. And when I got to carbon, I didn't give all 6 electrons the 1s hydrogen wave function. Why didn't I do that? Well, you already know that there's something called spin, right? Okay. And you already know that in the 1s state, you can only put in 2 electrons. And one of those electrons has to be spin up and one has to be spin down. And the same thing for all of these other states. One has to be spin up and one has to be spin down. Here's the electron configuration here for neon. That electron configuration just being the shorthand notation for the wave function in the 1 electron orbital approximation. Okay, so now we got to talk about spin. And what is this thing called spin? Well, spin is entirely a quantum mechanical phenomenon, right? It has no classical analogy that is accurate, that is correct. Spin is intrinsic angular momentum. It is angular momentum that is built into your particle. It's part of the nature of the particle. Electrons have spin. All right? Where does the spin, how do you see the spin? Well, if you solve the relativistic Schrodinger equation, which we didn't even write down, if you solve that equation, as Dirac did, well then one other quantum number drops out, and that's the spin quantum number. And that spin quantum number we call m sub s. Right? And m sub s has 2 allowed values. It can be 1/2 or it can be -1/2. So here we have a quantum number that's not an integer. All right? So it's 1/2 or -1/2. Now, what students often like to do is to think about spin as a classical analogy whereby if you have some electrons, so this is my electron here, and it's spinning around its own axis, right? The angular momentum vector is perpendicular to that plane, and if it's spinning in this direction, you might call this spin up. But of course, if it's spinning in the other direction, and then the angular momentum vector is again perpendicular to that plane, hey, you might call that spin down. Okay? This is a classical analogy. That is not correct. The electron isn't rotating around its own axis. But if it's going to help you think about that right now, okay, just remember it's not really correct. All right? Because this idea of spin is intrinsic angular momentum. It's part of the nature of the particle itself. All right? Okay, next time I'll tell you about Uhlenbeck and Hutschmidt and Pauli. See you Wednesdays.